Welcome everyone to the 2024 BioPhotonics Conference. Thank you all so much for joining us, and in this session you will hear from Nathan Brouwer, Sales Manager for the San Francisco Bay Area for MKS Ophir. Nathan earned a master's degree in electrical engineering and currently supports medical and industrial laser markets with power measurements and beam profiling demonstrations. Today he's joining us to discuss laser applications commonly found in medical surgery centers and doctors' offices. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all for me. Nathan, we appreciate you for taking the time to present at the 4th Annual BioPhotonics Conference.
All right, hello and welcome all to the BioPhotonics Conference. My name is Nathan Brouwer, and today we will be talking about lasers in medicine, why and how to measure your laser, power, profile, and position. Before we get started, I want to take a moment to thank our hosts at Photonics Media for this opportunity. First, I'll introduce myself and give you motivations behind the talk. Then I want to spend a couple minutes looking back on some history to remember where we've come from. I'll give you a rundown of where lasers are being used in medicine today, how laser energy affects human tissue, and what lasers are commonly used. Then we'll get into the bread and butter of the talk, why and how to measure your laser. What are the parameters to measure? Am I going to burn my sensor? Where do I start? I'll explain the 3 Ps and 5 Qs as learning tools. We'll talk a little bit about the difference between power and energy, how to choose a sensor. Then I'll help you understand the laser waste and how power density increases when focused with a lens. Lastly, we'll take a look at beam profiling, how to do it, and what to do once you have a profile. We'll have a good time, so let's get to it. In graduate school, I was very interested in biomedical applications and the nervous system. So this is why this topic is so interesting to me. I almost did biomedical engineering, but instead decided to pursue my master's in EE, which better prepared me for electromagnetics. So I'm very happy with my decision. I am a beam analysis professional at MKS Ophir, helping customers in the Bay Area measure their lasers. I've been in the laser and photonics industry for over a decade, and I estimate to have measured over 100 lasers. My contact information is provided, and I urge you to reach out to me with questions after the talk. Okay, I'm a bit of a history buff, so I'll attempt to give you the entire history of the laser in 2 minutes or less on a single slide. Ready? Go. In 1900, Planck derived his famous constant by measuring specific amounts of energy called quanta. These discrete packets of energy are called photons. He won the Nobel Prize for his work and famously said, "Entropy can be created but never destroyed." 17 years later, Albert Einstein built on Planck's work, contributing to the idea of stimulated emission. A photon hitting an excited atom releases 2 photons of the same frequency. This is how amplification is possible. In the 1930s, Fabrikant writes a technical paper on how to achieve stimulated emission. He coins the funny acronym MASER, or microwave amplification by stimulated emission of radiation. 25 years later, Charles Townes proves this theory and builds the first maser by exciting and resonating ammonia molecules, which demonstrated amplification of electromagnetic energy. It was very weak amplification, but it proved the theory. As you may or may not know, light and microwaves are both types of electromagnetic radiation, just on different parts of the spectrum. So in 1960, Theodore Maiman converted that discovery into the visible domain when he famously built the first laser at the Hughes Research Lab in California. The ruby laser was created by shining high-power flash lamp on a ruby rod with silver-coated surfaces. Goodbye maser, hello laser. This took microwave amplification to light amplification. Only 3 years later, Bell Labs invented the CO2 laser, which was a high-power gas laser. At this point, the horses were off to the races. For many years, the laser is said to be a solution looking for a problem. Applications expanded from metal cutting and welding in the 70s to material processing such as plastics, rubbers, foams, semiconductors, and organic materials such as skin and eyes. Speaking of eyes, I wanted to show how the laser revolutionized eye surgery. The first cataract on record was removed in the late 1700s in France. A curved needle is inserted into the eye, hooks the opaque material, and is pulled out. Then the eye is left to heal. It sounds painful. In the 1960s, Around the time of the first laser, a Colombian professor, Jose Barracour, was the leader curing vision problems by reshaping patients' corneal discs. He'd slice open the eye, remove the cornea, freeze it in liquid nitrogen, ground the lens into the correct shape before reinserting the disc back into the patient's eye, and this became the foundation for today's refractive surgery. Now, it's 1974. A young boy in Russia wearing eyeglasses takes a terrible fall off his bike and shatters his glasses. Lodging glass particles in both his eyes, he is taken to a leading optical doctor to remove the shards. The doctor is able to remove all of the glass, but he warns this boy that he may never see again. Several weeks later, the boy's corneas heal completely, and wondrously, his nearsightedness has significantly improved. The doctor discovers that this is because the radial cuts had flattened his corneas and changed the refraction. Dr. Fyodorov is fascinated by this discovery, and this leads him to develop a corneal shaping process called radiokeratomy, or RK surgery, which becomes wildly popular. The RK surgery shares similarities with today's LASIK. Remember, the first lasers were developed in the 60s. 20 years after that, a major breakthrough came when an Indian doctor, Dr. S, at IBM discovered that an excimer laser was able to remove living tissue without causing thermal damage to surrounding cells. 3 years of collaboration with IBM, another doctor, Dr. Stephen Trokel, applied this discovery at risk to his career, was the first to successfully reshape a human eye using a laser. Through continued testing, they found that laser surgery could be effective in treating nearsightedness, farsightedness, and astigmatism. Much later, Obama awarded Dr. S the National Medal of Technology and Innovation for his work on excimer lasers. Then, in 1987, a woman comes to the LSU Eye Surgery Center in New Orleans with a damaged eye. They offered her a new experimental laser procedure. She signs the waiver and becomes the first patient to receive PRK surgery. PRK, or photoreactive keratectomy, involves reshaping the cornea from the outside, then letting the epithelium layer of the eye heal itself. The surgery was a success, and the process was improved over the next 5 years. PRK surgery was first approved in Canada in 1991 and then in the US in 95, and remains in use to this day. And that's what I have. I got PRK back in 2016, and yes, my eyes were scratchy for a few days, but now I still see great, and I'm thankful to not have to wear contacts anymore. Meanwhile, 2 European doctors discovered a method using an excimer laser to create a flap in the eye, rather than removing the outer epithelium layer. The surgeons fold the flap out of the way to gain access to the cornea, perform the laser reshaping, and unfold the flap back when complete. This helped reduce post-surgical discomfort and accelerate the healing process. This innovation signaled the dawn of the modern-day LASIK eye surgery and was approved by the FDA in 1999. With continued advancements in technology, specialists now map the eye using a laser topography method for advanced accuracy, and they used ultra-short femtosecond pulses to limit heating, and they claim no recovery time procedures. These refractive procedures have been so successful that cataract surgeries include refractive corneal reshaping while they're in there. Cataract surgery uses laser pulses to break up the opaque buildup and has been considered one of the most successful treatments of all time in terms of completely correcting or reversing the cloudy vision by cataracts due to aging. Much better than sticking a needle in your eye. So this goes to show the evolution of a singular field in medicine through advancements in technology. Today, lasers have infiltrated nearly every aspect of the medical ecosystem. Surgeons perform exploratory surgery using lasers to see, cut tissue, and cauterize bleeding. Surgery equipment itself, like catheters, tubing, and stents, are mostly all laser cut, welded, and barcoded. Dentists use lasers to fight gum disease. Dermatologists use lasers for skincare and tattoo removal. Medical device companies like Boston Scientific are using lasers to make implantables like pacemakers and glucose monitors. Lab testing companies are using lasers to test your blood and saliva for all kinds of biomarkers. More recently, pharma companies are even using lasers to discover new drug therapeutics and other medical research. Here's the most obvious application: laser surgery, cutting and cauterizing. Current technical advancements have created these handheld laser tools. Instead of a mechanical steel scalpel and a heater to stop bleeding, now a single laser handpiece, the surgeon can rapidly switch between cutting mode and photocoagulation. These tools also have a super pulse mode that results in less tissue heating around the cut region. This helps with better healing and less scarring. Laser endoscopies can treat a host of internal conditions like vascular and GI issues. They can clear blocked blood vessels and break up kidney stones. The guided probe might have two lasers on it, one with a low power red laser to illuminate the area for a camera for the surgeon to see, and the other will be a high power invisible laser for the surgeon to go in and work on selectively shrinking a tumor, carving away abnormal cells or scar tissue. In oncology, doctors are using photodynamic therapy to treat cancer. The doctor administers a photosensitizing drug to the patient. This drug is targeted and taken up by hungry cancerous tumor. The photosensitizer sensitive light is then activated with laser illumination, which converts into toxic radicals that kills the cancerous tissue. In neurosurgery, the unresectable glioma used to be a dirty word. In other words, inoperable brain tumor. That used to be a death sentence. Today, not so much. The advancements in laser technology have given patients a chance at life. Now we can directly target areas inside the brain without having to cut or drill a hole in the skull. Monteris has developed a technology called NeuroBlade, minimally invasive robotic laser thermotherapy that uses MRI-guided surgical ablation. Really cool stuff. Let alone new surgeries, historical surgical methods use metal clamps, stents, plastic tubing, etc. This equipment, implantables and disposables, are almost all laser manufactured, processed, welded, drilled, and engraved. It all needs to be labeled and maintain sterilization. Laser printing a barcode on a tubing is a no-brainer. I know job shops that their sole business is to fabricate welded stents and catheters that are sold to hospitals and other medical facilities. Oral surgeons can use lasers to cut bone, cure fillings, and treat gum disease. You can also get a set of 3D printed dentures personalized to your mouth. The unique ability of lasers to target specific structures and layers of tissue make them a powerful tool in cosmetic and reconstructive surgery. Thus, lasers have made their way into dermatology offices and plastic surgery centers. So aesthetic lasers can remove wrinkles, treat acne, sunspots, and other vascular defects such as spider veins. They are huge in tattoo and hair removal. Laser resurfacing has been a major tool used in anti-aging treatments. These microburns cause the induction of new collagen formation, which is known to improve elasticity and skin thickness and lessen the effects of wrinkles and aging. Now prices are coming down, so you can even purchase an at-home laser for hair removal. So what happens when you shoot a laser at human skin? Well, it turns out it depends on a lot of factors. While it's true, a high-powered laser focused down to a very small spot will produce an extremely high-power dense beam that will instantly vaporize or ablate anything in its path. But more often, in medicine, we are generally talking about tightly controlling the laser beam properties to accomplish a specific task, such as delivering thermal energy or causing cell death through a chemical transformation process. Lasers come at various wavelengths, powers, and beam sizes and produce different effects in the body. And human tissue varies with even more factors. But essentially, laser light will either absorb, scatter, or reflect. And that turns out the absorption is the most interesting factor. By knowing what tissues will absorb specific wavelengths, we can selectively target certain areas. So that brings us to the term chromophore. Molecules or tissues that absorb light. Now these are wavelength dependent and therefore laser dependent. In the human body, the main chromophores are water, skin, and blood. The hemoglobin in blood and melanin in skin most strongly absorb light in the near infrared, most commonly found in nature at sunset. Water is an interesting chromophore because there's water in every cell of the body. Okay, so if you know your target chromophore in your tissue, or specifically add an absorption dye with that chromophore, you can selectively target certain areas. Talking about something, we should break down this word. Using light, photo, to create heat, thermo, to cause cell death, lysis. So the CO2 laser is one of the oldest, most robust types of lasers. In the body, the only chromophore is water. This makes it a great laser for surface treatments, but a pretty lousy laser for selective targeting treatments or more penetrative applications. Think about it like a flamethrower that can be focused onto a pinhead. Very useful in certain applications, but causes too much heating in other applications. The YAG, or ND-YAG, is the most pervasive, most studied, and most implemented laser in history. This is your do-it-all laser. Optically pumped, like the first ruby laser, the neodymium rod is specifically doped with various materials. It produces high-intensity pulses and efficiently frequency doubles, allowing for wavelengths at 1064, 532, 355, 266, and more. YAG lasers are used in many medical applications, such as endoscopy, urology, neurosurgery, gynecology, and dermatology. So the UV excimer laser is a go-to device in ophthalmology and dermatology. We talked about the laser eye surgery. This laser can penetrate more deeply into the body to target specific structures without heating the surrounding area. Therefore, we say it has a small heat-affected zone, or low Haas. So the CO2 laser, one of the oldest, most robust lasers in the body, and its only chromophore is water. It makes a great laser for surface treatments, but pretty lousy for selective targeting or more penetrative applications. Think about it like a flamethrower that can be focused down onto a pinhead. Very useful in certain applications, but causes too much heating in other applications. The YAG, or ND-YAG, is the most pervasive, most studied, most implemented laser in history. This is your do-it-all laser. Optically pumped like the first ruby laser, the neodymium rod is specifically doped with various materials. It produces high-intensity pulses, efficiently frequency doubling, allowing for wavelengths at 1064, 532, 355, 266, and more. YAG lasers are used for many applications such as endoscopy, urology, neurosurgery, gynecology, and dermatology. We have the UV excimer laser. This is a go-to in ophthalmology and dermatology. We talked about laser eye surgery. This laser can penetrate more deeply into the body to target specific structures without heating the surrounding area. Therefore, we say it has a small heat-affected zone, or low Haas. We have the argon ion gas laser. Is blue-green at 514 and used in a lot of medical applications due to high beam quality. But due to low efficiency, other lasers are beaming it out in select applications. It's still used in photodynamic therapy and other endoscopic procedures for examination and treatment of internal organs because it can be delivered easily through a flexible tube. The KTP, potassium titanol phosphate, is selectively absorbed by certain tissues such as blood vessels, making it a good choice for vascular treatment. The diode or semiconductor laser is a newer class of cheaper, more efficient lasers. These are used for photodynamic therapy, disinfection, wound recovery, photocoagulation, hair removal, and much, much more. Due to its low cost, these lasers are finding more and more uses. Lastly, I included the IPL. While technically not a laser treatment, it emits intense pulsed light at multiple wavelengths that scatter. Okay. Lastly, I included the IPL. While technically not a laser treatment, this emits intense pulsed light at multiple wavelengths that scatter and penetrate the skin at various depths. The IPL is effective for treating a broad range of skin conditions. Okay, so why measure your laser? For the safety of the patient, and it's the law. The FDA regulates both medical and non-medical lasers. They require a NIST traceable calibrated power measurement at least once per year. A laser is made up of components, and over time, these components wear out, degrade, or sometimes totally fail. A chamber can heat up, causing glass optics, metal mountings, or adhesives to expand and contract, causing shifts or misalignments. Dust and humidity in the beam path can cause all kinds of degradation issues to the optics in the beam path. Basically, lasers are great until they are not. And you want to know the minute a laser starts to degrade. Many lasers are invisible to the human eye, so you couldn't tell anything about the beam without proper tools. A small drop in power usually is an early warning sign before power and beam quality start to degrade. Once the process starts, it usually accelerates unless the user intervenes by servicing the laser. So first things first, in general, you need to get a calibrated sensor. This means it has been tested and comes with a certificate. Make sure you understand the calibration procedure. Sorry, my timing is off here. I'll go quick. So first things first, in general, you need to get a calibrated sensor. This means that it's been tested and come with a certificate. Make sure you understand the calibration procedure and calibration uncertainty. How to choose a sensor? We'll get to that in a minute. If we take a deeper look here, we took a green 532 laser measured at 1.8640 watts with a master or golden sensor. This is the gold standard, meaning this has been calibrated to the NIST golden reference unit. That's what NIST traceable means. Then we took another measurement with the same laser, but this time using your brand new sensor. It measures 1.8668 watts, which is only 0.15% difference. Pretty good, right? It is when you only need plus or minus 3% tolerance. So the sensor passed its test. And if you look down the right-hand column, it passed all the tests. The outgoing result was a pass, and the measurement uncertainty was 1.9%. This means you can be reasonably sure that your measurements will be within 2% of the real-world accuracy. So always get a sensor that is NIST traceable calibration, and keep your sensor calibrated by sending it to a calibration facility once per year. We have 4 calibration repair centers around the world, one in Utah, Israel, Germany, and Japan. Okay, you got your sensor. What do you do next? Hook up the power meter, bring in the laser, and fire the laser. Get your reading. Simple as that. In some cases, yes. If you have a thermopile sensor, it might be that easy. This is a coated metal disc that absorbs laser energy and converts to heat. Out on the edge, there's a series of thermocouples to measure temperature gradient, which is proportional to the absorbed power. These are nice because they are simple and easy to use. They work with a lot of lasers and they can handle high power. Here's one more very common type of laser sensor. The photodiode sensor also generates a voltage proportional to the laser light. It's slightly different photonic reaction, but these sensors are very linear, have a fast response time, and are usually low cost, making them a good option in cost-sensitive applications. The drawback is that they are sometimes too sensitive and require a lot of optical filtering to prevent saturation and damage. Okay, so you got a measurement. That's great. Is it stable? How much does it fluctuate? What is acceptable for your application? That little s, power stability, is always something you should think about monitoring. Fluctuating power or slowly decreasing power over time is an early warning sign that something might be happening. Okay, so you're measuring your power, but what if you have something like this? Did you notice the change? How about this? Instead of a continuous beam, what happens if your laser is producing a series of pulses? You can still measure power, but maybe a better question is, how do you measure pulse energy? Before we assumed the laser was just on, that is a fixed power, that is CW or continuous wave. What if your laser is pulsed? That is to say, the laser is off. Then it emits a pulse. The power rises to a peak and then decays back down. After a certain period of time later, another pulse arrives. These pulses are characterized by the duration or pulse width and repetition rate or time between pulses. As you can see, the average power of the pulse source does not tell you the whole story. And in fact, we generally talk about pulses in terms of pulse energy in joules. That is the total energy under the power curve. That is why a pyroelectric sensor is sometimes the best option if you want to measure pulse energy. The pyroelectric crystal generates an electrical charge proportional to the energy pulse absorbed. These can handle lots of pulse lasers, but the drawback is they can't measure average power. So it's important to choose the right sensor for your application. I work for Ophir. We have a huge portfolio of offerings for a broad range of lasers. We have sensors for pretty much every wavelength, power level, beam size, and pulse width. So which sensor do you choose? Well, any good vendor should be able to help you sift through all the options and find the right sensor for your laser. This is a tool I use called the Sensor Finder, and it is available on the Ophir website under a drop-down. I suggest customers come here to use the Power Energy Density Calculator. You can use your laser parameters to suggest sensors that have damage threshold below your laser's expected power density. We want you to choose the right sensor that is the right wavelength and right power level, but is hardened enough to survive the power density at the measurement plane. Or if your laser is pulsed, we need an energy sensor that can take the energy density of your laser. Most people think a laser beam travels straight. This is called collimated. As the laser leaves the cavity, it travels through space and time. While laser propagation in the ideal conditions can travel straight, called high coherence, in reality, nearly all lasers are slightly diverging. This means in application, you need a lens to focus or recollimate the beam. The sun is a great example of bulk power. You can feel it on your face, on your body. While it's very warming, it is unfocused. It doesn't burn you immediately. It's diffuse. But if you take a lens, like a magnifying glass, focus it down, it can get extremely hot and burn or melt quickly. Think about burning ants as a kid. Lasers are basically just very focused light. Like focusing sunlight in a magnifying glass, laser light is focused using a lens until it is very power dense. It's important to note that average power is the same throughout the beam, but power density varies with spot size. Laser power density is highest at the waist, where the spot size is the smallest. So let's head back into the lab. Now you notice that beam isn't perfectly straight. It comes out wide, it gets skinny in the middle, and gets wide again. This bears repeating. Power is the same along the beam path. So where do you measure? Won't you get the same measurement at location 1 or 2? I like to say yes and. Yes and you might damage your sensor. Helpful hint, measure power at a defocused position. In most material processing applications, the power is so dense at focus that will actually burn the sensor. So the recommendation is to defocus the beam by moving it out of focus position to a beam size of usually 5 millimeters or greater. You can use Zappet paper or thermal paper or a laser beam profile to determine its size along the optical path. Let's look at a real example. A medical instrumentation company called me up. They have a new laser welding station and they were worried because they had already burned their small 30-watt sensor. I had to go in person to explain to them why the waist of the laser is not a good place to measure your laser. We started out with Zappet paper to estimate the beam size. We ended up switching them to a pyroelectric sensor because the welder was emitting pulses, not a continuous beam, and had them measure well below focus. This stopped the damage from happening, and they even bought a camera to measure their beam size. That's when it really clicked for them. Seeing the beam size change in real time was the real light bulb aha moment. Okay, great. Now let's look at that second P, beam profile. So what's the best way to measure your beam? Just shoot your laser into the laser camera and the corresponding software should give you a beautiful image of your beam with a nice beam size measurement. Here's a perfectly Gaussian beam that looks really pretty. But wait, Nathan, didn't you just say don't measure your beam at the waist because you can damage your sensor? Even though average power will be the same anywhere along the beam path, we learned that power density is highest at the waist. So yes, I'm glad you're paying attention. But if you're trying to selectively target a certain area, heat a tumor for example, You need to see exactly where your beam hits focus and what your beam is doing at focus, the narrowest point along the beam. So yes, we need to measure the profile at focus. But first, we knock the power down to safe levels. We recommend a double wedge beam sampling system to maintain polarization while profiling a small sample of your beam. So here's what this looks like. You have your laser, and a little bit before focus, it hits a beam splitter, beam sampler, or wedge. It kind of acts like a window where most of the beam passes through onto a beam dump. But because it's at an angle, a tiny portion of the beam will be reflected onwards to the next stage. And again, the beam will transmit 96% of the energy through, or 99% if there's anti-reflection coating, and therefore 4% is reflected on towards the camera. Then there's an optional set of neutral density filter slides that can further attenuate the beam as needed. Camera pixels are very sensitive. For a 100 micron beam size, you need to get the total power down to the microwatt range. But when we use a sampling system and ND filters, it is possible to profile up to a 500-watt laser system, or in some cases, 5,000 watts. But when powers are that high, you need to be very careful about your beam dump systems. Okay, so now you have a beam profile, and it looks really ugly. Now what? The first step is to see your beam, get beam size measurements, and then start to evaluate the beam quality. What kind of beam is it? Is it a regular Gaussian? Is it a flat top? Does it have hot spots and multiple peaks? Okay, here's a screenshot from a customer demo who gave us permission to share results. This is a beam from a real live welder. They were not getting good results with their welds. Notice the double peak on the X profile and the lumpiness and roll off on the Y. All the intensity seems to be concentrated in the upper left quadrant. Here's another example of a very peaky beam. Notice the middle just started to saturate. You can see the white spot starting to form in the red center. This is generally not good. So when this types of thing happens, you generally want to inspect and clean your optics, verify the alignment, scan through your Z distance and find focus, rotate the laser crystal, which is something internal to the laser. You might need to call your laser service technician for that. So that's exactly what, in this case, the laser service technician was able to rotate the laser crystal to a more optimal alignment, and the beam quality improved greatly. It still doesn't look pretty necessarily, but if you look at the X and Y profiles, you can notice that they are all within a certain range. This indicates that it is a reasonable flat top, and this was confirmed through experimentation that the welder started to perform better. So we talked about the camera-based beam profilers, why you want to know about beam size, uniformity, and modes. The Ophir profile has a wide offering of beam profiling and other beam analysis equipment for a broad range of lasers. Fortunately, we're about out of time, so we won't go into the other beam analysis methods now. So in summary, better lasers can selectively target certain areas deep into the body with limited damage and heat to surrounding areas. This is achieved by being intentional about the energy absorption, the chromophores, focusing to very small spot sizes, and using ultra-short pulses for low heat effective zones. For the patient experience, laser technology in medicine has led to minimally invasive procedures, less risk, optimal clearance of disease, shorter recovery times, and improved patient satisfaction. Monitoring and measuring these lasers is critical to repeatable performance and critical to patient safety, and the FDA requires laser calibration. So when people ask what we do, I never know what exactly to say. What works for me is I tell them Ophir is like the measuring tape for lasers. Many lasers are totally invisible to the human eye or too small for the eye to see anyway. It is nearly impossible and very dangerous to burn paper to try to measure your burn spot. We supply hardware sensitive to these lasers and bundle powerful software around it. The bottom line is that products let customers know what is going on with their laser and allow them to prove or disprove that their laser is in tune. So thank you very much. Hope you have enjoyed this talk. Feel free to contact me after with any questions. I'll flash some of the references up here.
Thank you so much, Nathan, for joining us to discuss lasers in health and medicine. Just to echo your statement real quick to everyone joining in our audience, if you haven't already, you can type your questions and comments into the conference chat box. And do not worry, if you've not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 4th annual BioPhotonics Conference. Thank you all so much for joining us.